Welcome to the course on biostatistics and design of experiments. We will continue with problems on Anova. I am spending a lot of time on Anova with examples because that is a very important topic, and you should be able to do problems related to Anova without any difficulty. That is why I am trying to give as many worked out examples as possible with Anova, because we are going to now look at one way Anova, later on we will look at two way Anova, and then we will look at interaction between those two different groups or two ways and so on actually. So, let us again continue. So, 5 different growth media were tested for bacterial production of a biopolymer. So, because biopolymers like glucons okay, are produced with bacteria, like you have linear glucons which are extracellular, you can have cyclic glucon which are intracellular. So, a lot of bacteria produces biopolymer. For example, PHB is a biopolymer, just like glucons, PHB is a biopolymer. There are many biopolymers. Okay, so we tested 5 different media for the production of these biopolymer, and you can see the results, 5 different experiments. So, you have 5 different experiments, 5 different media. Now, we want to know these are the results of the biopolymer production. It could be in terms of say milligram per liter, okay. So, that comes to about 0.1 gram, it is quite low, whereas if you take linear glucons you may get in 30, 40, 50 grams per liter. Some glucons are produced with the very low quantities, okay. So, 100 milligram per liter is what you are seeing. We are having 5 different media. So, this is called a one way Anova, because we are looking at only one way, okay, or one parameter or one group, okay, but these are all repeats of these. How do we do it? So, we have talked quite a lot. You should be able to do this problem without any difficulty, but let me also work out once more, okay. The total sum of squares is x, that means each of these. In this particular example we have 5 and we have 5, so 5 into 5. So, each of these data minus x double bar is the overall average, okay, that I will call it the global average, okay. X double bar is the overall mean, that means you add up all the 25 data points, divide by 25, you will get the overall average. So, this is called the total sum of squares. Now, between sample sum of squares, so we have 5 different situations, right. We have 5 different media. So, there is going to be an average for each one of them. So, we have a global or total average. So, subtract from each one of these average, square it up, then multiply by 5, because we have 5 elements in each one of these. Then when you add up, that will give you sample sum of squares. We have 5 sets of samples or 5 sets of groups or 5 sets of independent variables tested. So, in this particular case we are going to multiply by 5. So, for each one of them there is going to be an average, okay, and then you subtract from the total overall average, square it up. Now, there is something called within sample sum of squares. This is a indication of the error, okay. So, although you should get this as the value, you are going to get different values, right. So, for example, we have 100, 100, 99, 101, 100. So, there will be an average. So, what is the difference squared from the average or mean? You square it up. For each one of them you take the subtraction from the mean of that particular group, square it up and then add up all of them, okay. So, when you do that, that is called within sample sum of squares. This is an indication of error. So, ideally we should have this within sample sum of squares as small as possible, so that the between sample sum of squares look large, because we are going to later on calculate the f value, that means divide the mean sum of squares of between divided by within, okay. Now, total sum of squares is also equal to this plus this, between sample and within sample. So, sometimes we do not have to calculate this, from these two calculation we can do that. Then we create the Anova table. Before that, let us look at the hypothesis. The null hypothesis is sigma 1 square is equal to sigma 2 square is equal to sigma 3 square is equal to sigma square 4 square to 5 square. That means all these 5 sets of samples come from the same population. So, the variances are equal, or the alternate could be one of them are not equal. So, that is the alternate hypothesis. So, we can have a p value and this will be a two-tailed test. Okay, so, between sum of squares you calculate from here, and then within sum of squares, which is called an error, calculate from here. The degrees of freedom is n1 in your problem. We have 5 sets of groups or 5 sets of media we are testing. So, degrees of freedom will be 4. Now, the total will be 25 is the total number of experiments minus 1 is 1, that is 24, this will be 4. So, error will have the degrees of freedom as 20. Now, how do you calculate F1? F1 what you do is you do F1 is nothing but mean variance. So, mean means BSS by N1, mean means WSS by N2. Now, F is given by F1 by F2, you are dividing by error. So, if the error is very small, F will come out to be very large, and then we compare with the table F for N1 and N2 degrees of freedom, and then you accept or reject the null hypothesis. Okay, let us go back to our problem. So, we have the data here given, average of each one of these media will be like this. So, we get this as 100, 102, 105.2, 98.8, 119.2. So, we take the grand average, this is overall average. Okay, so, between sum of squares is very simple. What do? You take this minus this square multiply by 5. Why 5? There are 5 terms here, right? And then you take this minus this square and multiply by 5. So, you get like this, right? This minus this square multiply by 5, this minus this square multiply by 5, then you add up all of them. Okay? So, 5 into 100 minus 105.04 square, 5 you are multiplying because there are 5 terms like that. Okay, then you add up all of them, that will come to between sum of squares. Now, how do you calculate within sum of squares? That is simple. I said look at each one of the average and then see each term how much it is varying. So, 100 minus 100 square 0, 100 minus 100 square 0, 99 minus 100 square is 1, 101 minus 100 square 1, like that. So, this will be 119 minus 119.2 square, like that. Then add up all of them, that will give you within. How do you calculate the total sum of squares? Each term 100 you subtract from the grand average or the global average square, 100 minus 105.04 square, like that, So, you will get 25 terms, add up all of that, that will give you total sum of squares. You see, if I add the between sum of squares and within sum of squares, I will get the total sum of squares. 1370 plus 90 is 1460. Okay, then you create your Anova table. Okay, how do you make the Anova table? So, the sum of squares 1370, from here between, that is media, and then within is within is 90.4, so 90.4, and then total sum of squares 1460. 60. Now, media, there are 5 media. So, we have 4 degrees of freedom, and then total you have 25 data points. So, 24 minus 4 is 20. So, error has 20. So, how do you calculate mean? This divided by this divided by this. Okay. Then how do you calculate the F ratio? You take the mean of this divided by the mean of this. So, we get F ratio. Do you understand? So, that way F value is much larger than the F value calculated here, 2.87, is the table value for 4 and 20 degrees of freedom, for 4 and 20 degrees of freedom 2.87, whereas we calculate 342.6. So, we can reject the null hypothesis. So, if you look at the media average, the E gives you the highest. So, obviously, I would say media E is the best, because E gives you the highest average value. Do you understand? E gives you the highest average. That is how we would do this problem. Okay, so, we have done many times the one-way Anova, as it is called, because here we are considering only one media, that is why it is called the one-way Anova. So, we make use of these tables. We have looked at these tables many times. So, you should be comfortable for 95 degrees of freedom as well as for 95%, confidence as well as 99% confidence, and then we have the numerator degrees of freedom, denominator degrees of freedom, and so on. Okay, we can also use t-test for this, but then how do you do the 2 sample t-test? We have 5 media, right? So, we have to do 2 at a time. So, it is time consuming. So, as you can see, the one way ANOVA is more powerful than a 2 sample t-test, because it can look at all the mini samples in one go. That is the advantage of this actually. Okay. Now, let me introduce something called replication. Replication is a repetition of an experimental condition, like in when I am doing a bioprocess experiment. What do? I do the reaction with the media 1 and finally find out the biopolymer quantity. Again I do the reaction from the beginning. Okay. So, that is repetition of an experimental condition. So, multiple experiment runs with the same factors. So, if I am using some pH, I am using some temperature, I am just changing media. So, A, then I will do the whole experiment, extract the polymer, weigh the polymer and come up with 100 milligrams per liter. Again I do the same experiment in the fermenter, and again I extract the polymer, weigh it, and again I get another 100, like that. That is called repetition, replication. But that is not same as the repeated measurements. What do you do in repeated measurement? Suppose I am measuring the amount of biopolymer in a high pressure liquid chromatography. I take the sample, measure it, get the amount of biopolymer. I again take a sample, measure it. So, that is not same as replication, you have to remember that. So, whereas in replication you do from the beginning, keep all the parameters and then do the whole experiment and finally get the amount. Whereas in repeated measurement you take one sample, then again another, take a second sample, third sample, and looking at the amount of say biopolymer, but you are not repeating the experiment from the beginning. Okay. So, replication is repeated measurement of the same item is called repeat, whereas replication is multiple experimental runs. Okay. There are 2 more terms, one is called the repeatability and the other is reproducibility. So, repeatability is more like testing the instrument. I take a sample and check it out on the instrument, then again I measure, take the sample, check it out on the instrument. So, that is more like checking the repeatability of the instrument at the same condition. Whereas, replication is more like reproducibility, the entire experiment is repeated, entire experiment from the beginning. You keep all the variables, set all the variables and do the experiment, do the extraction, measure the biopolymer using a chromatography and so on. So, the entire experiment is duplicated by the same researcher or by someone else. So, that is called reproducibility. So, reproducibility is same as replication, but repeatability is repeating the analysis twice or thrice and so on actually. So, reproducibility you are trying to seeing whether operator 1, 2, 3 are able to reproduce the same experiment. I give the same experiment to 3 people and see whether they are able to reproduce it. So, I may have a situation where one operator, second operator almost able to reproduce, whereas third operator is not able to reproduce. Okay. So, the repeatability is different from reproducibility. So, in reproducibility you are starting from the beginning and doing the whole experiment and measuring your dependent variable. So, that is also called replication, whereas in repeatability we may take only one sample and check the measurement. So, it is more like you may just do the assay twice, thrice from different samples, or you may make an instrument measurement. So, it checks your error or consistency. So, the repeatability tells you the consistent of the repeated measurements of an instrument or a part at same condition, whereas reproducibility is the entire experiment is duplicated. Are you able to reproduce? Is somebody else able to reproduce your experiment? If somebody else in a different location is able to reproduce. So, both are very important, repeatability and reproducibility, both are very important actually. So, in the example which we looked at, the biopolymer production, the previous ANOVA example. So, it is a reproducibility, okay. It is a reproducibility or it is also called the replicated experiment. Okay. Now, let us look at this particular problem. Okay. We can look at it as a replication. So, we have 5 mice, okay. They were tested on 4 different types of dietary food, and then after 3 months their weight gain was measured. So, mouse 1 when was given LF gained a weight of 20, when it was given this low fiber, medium fiber, high fiber, very high fiber. So, each mouse from a litter was tested, okay, and then the weight gain was measured actually. So, these are the experimental results we have. Okay. So, we can do the same ANOVA. So, here we can do 2 types of ANOVA. One is based on the type of food, another is based on the mouse, okay, because each mouse could have come from a different litter. Okay. So, we could have one way based on the type of food, whether it is a low fiber, high fiber, medium fiber, very high fiber, or other one could be based on the litter from which the mouse have come. So, is there going to be a difference in type of food? Is there going to be a difference in the litter from which the mouse has come? So, we can have 2 different situations, I will call it 2-way ANOVA. So, we have the mouse litter, these are the food. So, I can have an average for food, I can have an average low fiber food, medium fiber food, high fiber food, very high fiber food. The grand average or overall average, again I take an average of all these. Okay. Now, we can also have average along the rows. Okay. So, this is an indication of the litter of the mouse. So, 19.25 is the average of this 4 items, 19, this is 19.75 average of this row, and so on. Okay. And when I take an average of all these, I should be getting the grand average. Okay. Now, we have a food average, we have the litter or mouse based average. Now, how do you calculate sum of squares for food? 20 minus 19.5, 20 minus 19.55, square it up, multiply by 5. Okay. Why do I multiply by 5? Because there are 5 terms. So, 19 minus 19.55 square multiply by 5, 17.4 minus 19.55 square multiply by 5, 21.8 minus 19.5 square, then add all these, I will get food sum of squares. Now, for litter also I can do, what do I do? How do I get this term? 19.25 is the average of this row, right, multiplied, sorry, minus 19.55, square it up, multiply by 4. Why do I need to do 4? Because I have 4 terms here, right. So, 19.75 minus 19.55 square multiply by 4, 19.25 minus 19.55 square multiply by 4, 20.5 minus 19.55 square multiply by 4, 19 minus 19.55 square multiply by 4. So, if I add up all these, I will get litter sum of squares. Okay. How do I calculate total sum of squares? So, from the grand average I subtract each one of these terms, square it up, 20 minus 19.55 square, 19 minus 19.55 square, 20 minus 19.55 square, like that, you know. Then add up all the terms, I will get the total sum of squares. So, we have food sum of squares, one based on litter, one based on total sum of squares. So, if I subtract food sum of squares, litter sum of squares from total, I should get the error sum of squares, that is coming to 28.3. Do you understand? So, I have got one more variable situation here, not only the food, I also want to see whether the mouse responds differently. So, just like I take average for the food, I take the average for the mouse, each one of the mice, because each one of the mice could be coming from a different population of the species. Then I subtract, square, multiply by 4 because there are 4 terms, then add up all of them, I will get litter sum of squares. Just like food sum of squares, I get litter sum of squares. So, you know how to do the total sum of squares. So, error sum of squares comes out to be TSS minus food sum of squares minus litter sum of squares. Now, I make my ANOVA table. Look at this ANOVA table, it has one extra term. Food sum of squares is 50.94, liter sum of squares is 5.7, error sum of squares comes out to be 28.3, total is 84.95. Now there are four different foods, so DF is 3, there are 5 different liter or mouse, so 4, there are 20 data sets, so TSS is 20 minus 1, so error is 19 minus 4 minus 3, 12. So mean 50.95 by 3, 5.7 by 4, 28.3 divided by 12. So if I want to get F, 16.9 divided by 2.35, that comes to 7.2. Then for liter 1.4 divided by 2.35, 0.6. Okay. So for 3 and 12 degrees of freedom, 3 and 12 degrees of freedom at 99 for example, 3, let us go to 3 and 12 degrees of freedom for 99 is 5.95. Okay, 5.95, you get an answer of 7.2. So your calculated value is much larger, so reject the null hypothesis. So dietary food has a significant effect gain at 99% confidence interval. Now let us look at this one. How did you get this? Liter divided by this 0.6. So this has a 4 and 12 degrees of freedom. Let us go back to our F table at 99%, 4 and 12 degrees of freedom, 5.412. So you need to get 5.412, you got only 0.6. Obviously liter has no effect, only food has an effect on the or dietary fiber has an effect on the weight gain, but the liter from which each mouse came has no effect. So you are very happy about it, because you do not want that effect coming into the picture. And out of these food, which one is the best? Obviously this VHF is the best, because the average is 21.8 here, right. So VHF is the best food for weight gain for the mouse, and food has an effect here, whereas liter does not have an effect. We will call this a two-way ANOVA, because we have two different situations. One is food, 4 columns we have, low fiber, medium fiber, high fiber, very high fiber, and then 5 different liters of mouse. So we checked whether the food has an effect, calculating the F value, liter has an effect, calculating the F value. So every time we divided by the error, so we find the food has a much has an effect, because the F value we calculate is higher than the table value, whereas liter has no effect, because the F value which we calculated is much less than the table value. Okay. So one important point you need to know is your error sum of squares is small, so when you divide you get a large F. So in order to get good error sum of squares, small error sum of squares, your DF for error also should be large, then only you will get a very small mean sum of squares. Do you understand? Do you understand the story behind this? Okay. Okay. Let us look at another problem which deals with the a two-way situation. Okay. So we have 2 drugs, it is being tested on 3 different age groups. We call it the old age group, we call the adult age group, we call the infant age group. So we have the age group coming 3 different levels of age group, 2 different drugs X and Y. They are supposed to reduce the lipid levels, okay, mg per ml in the blood. So we tested on 6 volunteers, okay, and these are the results. In it reduces in some cases, it increases slightly in this case. Now you can look at, one is related to age, another one is related to drug. Okay. One is related to the age, another one is related to the drug. Now if I look age average, so I just column wise I can put, right, 4 plus minus 3 divided by 2, minus 1 plus minus 10 divided by 2. So these are the age average. Then if I took the global, this is the global average, total average, this plus this divided by 3. You understand? Now drug average means you add up all these divided by 3, because here we have 3 situations. Okay. So it is minus 20, minus 21 by 4, 17, 17 by 3 will be minus 5.66. For this minus 30, minus 10, minus 3, that comes to minus 43 divided by 3, minus 14. So this is the drug average for each one of the drug. Now how do you calculate the drug sum of squares? You take this age sum of squares, you all know. Okay. So you have the age average minus 10 square multiply by 2, because there are only 2 for this. Okay. So then add it up. Okay. So you understand 0.5 this, okay, minus 10 minus 5, that is 10.5 square multiply by 2. So these are all these sum of squares we get, we add up everything, this will give you the age sum of squares. Okay. So okay, let me again show it to you. Drug average, how do you get it? Okay, 3 how do you get the drug average? We have this plus this plus this divided by 3. How do you get drug sum of squares? We have 5.66 here, global is minus 10, so minus 10 minus 5 square. We are multiplying by 3 because there are 3, okay, terms here. So what do you do? Like that you get. Then for this what do you do? Minus 10 minus 14 square multiply by 3, you get this term. Okay. So that is how you get. Okay. How do you get the age average? 2, because there are 2 terms. Okay. 10 minus, that is minus 10 minus 5 square. So you get this term. Then in this particular case minus 5.5 minus 10 square multiply by 2. In this particular case minus 25 minus 10 square multiply by 2. Add up all of them, you will get age sum of squares. Okay. Then similarly you got drug sum of squares. Now total, you all know how to do that, right? Very simple. So minus 10 is your global average, minus 4 square, minus 10 minus 1 square, minus of minus 1 is plus 1, so 9,981. Then add up all these, that will give you total sum of squares. Okay. So you got total sum of squares, you got drug sum of squares, you got age sum of squares. If you subtract both from this, you will get error sum of squares. You understand? So let us go to our Anova table, total sum of squares, age sum of squares, drug sum of squares, error is got from subtracting these 2. Now total is 6 data points, so degrees of freedom is 5, there are 3 ages, so degrees of freedom 3 minus 1, there are 2 drugs, so you get 1. Okay. So error is 5 minus 2 minus 1, that comes to 2. So mean sum of squares 711 by 2, drug is 112 divided by 1, error is 2.33 divided by 2, 1.16. Now for age F 355 divided by 1.1, for drug 112 divided by 196. Now for this we get F2, 2 at 95%. Let us look at it. 2, 2 at 95%, yeah, 2, 2 at 95%, you see 19 degrees of F value comes out to be 19, right. Okay, 19. So this is large. So obviously age has a significant effect, because we have to reject the null hypothesis at 95%. Similarly for 1, 2 F, I get 18.5 from the table, and here you have 96.58. So obviously we reject the null hypothesis. So statistical significant differences between the drugs in lowering the blood lipid level, statistically significant difference between the way the people from different age groups respond. Okay. So obviously the people respond differently for the drug. There is a statistically significant difference between the drugs, because both are significant. So here this is called a two-way ANOVA. One is one way is the drug, or one level is drug, other way or other level is the age. We have 3 age levels: infant, okay, adult and old, and we have 2 drugs, one is X and Y. Both are significant, because when I divide by the error, both come out, the F value comes out to be very large when compared to the table value. Okay. Now I want you to think another important thing. there appears to be an interaction between the drug and the age of the volunteers. Why do I see this? Have a look at this. Okay. Now, in infant, drug X is increasing, whereas drug Y is decreasing in infant. If you go to adult, okay, drug Y seems to have a bigger effect than drug X. Okay. And if you go to the old age, drug X and Y are almost same, 20 and 30. So, obviously, it is not only drug has an effect on there is a variation in the age group, there is a variation in the performance of the drug, but there seems to be some sort of an interaction the way drug acts on different groups, okay, the way drug X acts on different groups, the way drug Y acts on different group. Okay. So, let us look at this drug X average, it is minus 5.66, drug Y average minus 14.3, you see. So, it seems to be acting very differently on different populations. Okay. So, that is called interaction. Okay. What is interaction? We will spend some time on what is interaction. Suppose I am doing looking at a product yield in a fermentation, I am changing temperature and pH. So, at one pH 3.5 I am changing temperature, I get a product yield like this. I am doing at pH is equal to 4, I get the product yield like this. Okay. So, they look almost parallel. So, if I want to develop a model, x1 is variable 1, that is temperature, x2 is variable 2 pH, I can develop a model, regression model y is equal to c plus ax1 plus bx2 plus error. Okay. So, there is no interaction between temperature and pH, and this is called an additive because you have ax1 plus bx2. Okay. When I change temperature at one pH, the yield goes up like this. When I change temperature at another pH, yield goes up like this. They look almost parallel. Now, you can have situations like this. Okay. At pH 3.5 yield is going up, at pH 4 it is not going up as much, but it is sort of flattening. So, obviously, at pH 4 there is it depends differently for temperature when compared to pH is equal to 3.5, and this type of situation we can't write equation like this for y yield, we may have to write c x1 plus bx2 plus d x1 into x2, this is called interaction x1 into x2. As you can see here, at pH 3.5 consistently going up when you change temperature, whereas at pH 4 it is going up and then sort of flattening out, right. So, it is not like this situation. So, obviously, there is an interaction between pH and temperature, or you may have a situation like this, pH 3.5 it is going up like this, at pH 4 when you change temperature it is going up very high. So, obviously, there is an interaction, and you may have to develop model like this for interacting situations like for this or for this, whereas if you look at this it can be an additive model, there will not be terms like x1 x2, and that is what is happening in your drug versus people also. Okay. If I plot same thing, you may get same problem, right. Drug X is like this on infant, adult, old, drug Y is like this on infant, adult, old, and obviously there is a difference, but we cannot look at really interaction, but there is definitely an interaction. I want you to see this, the drug Y behaves very differently between adults, whereas it works very differently with infant, whereas it works very differently on old when compared to drug X. So, obviously, there is an interaction between drug X and Y. We will talk more about interaction in the next class as well, okay, because that is very important. Interactions can happen quite a lot between drugs and type of race. Some drugs work differently on Caucasian versus African versus Asian versus European. Some media works differently with different types of bacteria, pH, temperature, where interactions are possible, and so on. Actually, we will talk about interactions and how to look at interactions using analysis of variance techniques in the forthcoming classes. Thank you very much.